right, starting 12.4, we should know, I think it's 8 different derivative rules by now, including product rule, quotient rule, and chain rule, right? And so I've put a worksheet on Canvas that you're welcome to print out and fill out as many times as you need to with all of those different derivative rules. Those rules you need to know and you need to be able to apply for all of our exams from here on out. You will not be given those rules on any test or exam or final exam in this class. So make sure you know those, I think it's 8 rules. Now, we're going to learn a couple more rules now. These are the only rules that you will be given during your test. So I have a formula sheet that I will provide for you on your Chapter 12 exam that has these derivative rules. These derivative rules are the derivative of e to the x, the derivative of a to the x, which a is just any positive number except for 1. And then really, these next two are just the chain rule version of the first two. So the first one, I called it number 1a, is e to just an x. But this last one is really e to g of x. So I have another function inside my function. I have a composition function. So it's not just e to the x, it's e to a bunch of stuff besides x, right? And so we have to do chain rule. Same thing with the number 2b. It's just a chain rule for a. Instead of a to the x, it's a to the g of x. There's a function inside of another function. So really, all you would have to do is really look at these two. Because remember, if you do the chain rule, no matter what, it always works out. But if you just try to use the first two, and there's more than just an x in your exponent, then you would not get the same answer. What I've also done for you is provided you with proofs of these different derivative rules. Instead of just telling you what they are and you believing me, some of you might be interested in where and how they came about. And so I've written out the proofs for each of these derivative rules, and I've also posted them in Canvas. So you might want to take a look so you can see how we came up with the rules. The rule is that the derivative of e to the x, you know e is just a number, 2.71 something. But it's an exponential function because my exponent has a variable in it. If I have e to the x, then the derivative of e to the x is just e to the x. So that's an easy one to memorize, right? Now, if it was more than just e to the x, then I would have to do the derivative of the outside, so e to the whatever the exponent is, keeping my exponent the same, and then making sure I multiply by the derivative of that inside function, or that exponent, g prime. So that's just a chain rule of the first rule. Now if I have a number raised to the x, so any positive number besides 1 and besides e, so for example 4 to the x, it's still an exponential function because my variable is up in my exponent. The derivative for this exponential function is the natural log of a, whatever your base is, times a to the x. So it's your original times the natural log of your base. However, if your exponent is more than just an x, well then we would have to go down and use the chain rule version, where we have the original times the natural log of your base, but then don't forget to take the derivative of your inside function, your exponent in this case. All right, so now that you've seen the rules and you can go and look at the proofs of those rules, let's do an example. Example number 1 says find the derivative of each function. Number 1a says we have y equals e to the 5x. Hopefully you noticed that it wasn't just e to the x, it's e to the 5x. So there's a little more inside here than just an x. To me, that tells me that I have an inside function and I need to do chain rule. Chain rule says I do the derivative of the outside. In this case, my outside function is my e. And we just saw that the derivative of e is just e to the whatever the exponent is. And we're going to keep that 5x, the inside function, the same at first, right, when we do chain rule? So I have e to the 5x, but then I have to make sure that I don't forget to take the derivative of my inside. So the derivative of 5x is 5. So the derivative of e to the 5x is really 5e to the 5x. All right, look at b. b says I have a function s equals 3 to the t. If you don't like the s's and the t's and you want to look at it a little more comfortably, if you like x's and y's, it would look something like this. Don't always, though, get so used to using x's and y's because variables can change, right? But this might help you recognize that this is going to be rule number 2a. I have a base that's a number raised to an x exponent. So if I have 3 to the t, right, then my derivative is 3 to the t times the natural log of my base, which is 3. So 3 to the t times the natural log of 3. You could have written it the other way because the natural log of 3 is just a number, so you might like to see that as a coefficient in the front. Just be careful not to multiply the 3 and the 3 and call it natural log of 9 to the t. Order of operations says we can't do that. We're supposed to do the exponents before we multiply, so don't be careful with that. So I always like to put my natural log in the back so that I don't accidentally do that, or make sure you put parentheses around the natural log of 3. That is just a number. All right, look at C. I have y equals 10 times e to the 3x squared. Well, I notice that I have this 10 coefficient, and this 10 is just a number, right? And then I have another piece that has an exponent to it. So I have a coefficient, a constant, a number in front that I should be able to just leave in front. Then I should be able to find the derivative of the rest of my problem, e to the 3x squared. I noticed that it wasn't just e to the x, it was e to a whole bunch of junk, right? And so as soon as I see all that junk, I know it's going to be chain rule. Chain rule says I take the derivative of the outside function, e to the junk is just e to the junk. But then I have to make sure I multiply by the derivative of that junk, the derivative of my inside. So the derivative of 3x squared is really 6x. So my final answer, when I combine some of my coefficients, is 60x times e to the 3x squared. So using some of our rules up above to apply the derivative rules to any of those different exponential functions. All right, let's look at a few more here. Let's look at D and E. D says we have s equals 8 times 10 to the 1 over t power. You might have noticed, now be careful, we can't multiply the 8 and the 10 and just call that 80, right? Because order of operations says we have to do exponents first. But I did notice that the 8 was just an 8. It was just a number, a coefficient, a constant in front that I should be able to just leave out in front and then be able to multiply back through in the end. I also noticed that in my exponent I had a variable, but it was in the denominator of my exponent. So I'm actually going to move that up and call it t to the negative 1. So 10 to the t to the negative 1 power. This now has a base that's a number and an exponent that's a variable. So to me, this looks like rule number 2b, doesn't it? I had my 10 as my base, but then I had a whole bunch of stuff up in the exponent. It wasn't just a t, it was t to the negative 1. So I'm going to use that rule. That rule says that I have my 8, and then when I take the derivative of b to the g of x, do we call it b? Oh, we called it a, right? A to the g of x. I have my original function times the natural log of my base, but then don't forget we have to take the derivative of that exponent. So if I bring forward the negative 1 and I subtract 1 from my exponent, I really get negative 1t to the negative 2. All right, now we have to try to make this look as nice as possible. I noticed that this was an 8 and this was just a negative 1, so I could really call that negative 8. I have my natural log of 10. I want to take this negative exponent and make it positive by just dropping it down to the denominator, but still in the exponent of my 10. So that's down here. And then I have this t to the negative 2 that I want to drop down to my denominator of the whole entire problem. All right, so my derivative then is negative 8 times the natural log of 10 times 10 to the 1 over t squared. Whew, that one looked a little bit tricky, so you have to be careful on that one. All right, last one, let's look at E. Y equals 2 to the pi. So what rule is that? Oh, be careful. I hope that you didn't say rule 2a, a number to a variable exponent. Even though it looks like a variable, isn't pi just a number? So isn't this really y equals 2 to the 3.14 something, 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 something? So let's simplify it a little bit. Let's just say it was y equals 2 to the third power. And I asked you to take the derivative of y if y is 2 to the third power. Well, isn't 2 to the third power just a number? 8. And so if I take 2 and I raise it to pi, isn't that just a number? And hopefully you recognize that the derivative of any number is just 0. So the derivative of 2 to the pi is really just 0. So be careful not to use a rule that doesn't apply. Don't let them trick you by using that pi symbol instead of a variable there.